Good evening and welcome everyone to New Space Chicago. Thanks for coming this evening. We are a networking organization, 501c3, devoted to supporting space entrepreneurship in the Chicago area and Midwest region. And we hold regular networking groups, regular networking events, and we bring in speakers from time to time to talk about relevant subjects. So this evening, we are very happy to have Robert Hoyt of Tethers Unlimited with us this evening. He is a relentlessly inventive technologist and executive with expertise in advanced space technologies, additive manufacturing, plasma physics, and scientific algorithms. He co-founded Tethers Unlimited in 1994 and has built it into a multi-million-dollar space and defense R&D firm. His pioneering advances in small satellite technologies, as well as in-space manufacturing and robotic assembly capabilities. He also co-founded ScienceOps Inc, a big data algorithm and web analytics firm, who was acquired by Acquisio in 2012. Over the past 26 years, he has pioneered the development of technologies for in-space manufacturing and assembly of space systems, affordable mitigation of orbital debris and radiation belts, propellantless propulsion for spacecraft, and mesh network communications for satellites. We're very happy this evening that he's agreed to talk to us about challenges in building an in-space economy and building a successful space company. So Robert, if you want to turn on your camera and mic, and then maybe you can share your slides, and away we go.
Okay, let's see. Oh, fractal. Can you see this now?
Can you expand to full screen?
Yeah, can you see that?
Yes.
Okay, cool, well, thank you. Thanks y'all for showing up. So today I'd like to talk about work we and a handful of others are doing in the space industry, trying to stand up an in-space supply chain so that we can create kind of a new economic sphere out beyond the surface of Earth, where the challenge part of the challenge right now is that the infrastructure we have supporting the space industry is entirely earthbound. Everything that goes up into space gets manufactured here on Earth and then shipped up into space. And additionally, the customer base for space businesses is also almost entirely earthbound. And kind of the dirty secret of the space industry is there's really only two markets where significant revenue is generated. One of those is Earth observation, pictures and radar of the Earth. And the other is data transport, satellite communications, satellite TV, those sorts of things. And for both cases, the customer base is all on the ground. What we'd really like to do is help create a functioning marketplace and economy out in Earth orbit and beyond, so we can help to expand our overall economy and help to support the expansion of humanity out into the solar system. So in trying to create an in-space economy, there are a number of different markets that a variety of different ventures and organizations are pursuing, ranging from propellant depots to asteroid resources to in-space manufacturing of materials and lunar resource development. But each of these markets by itself has kind of a chicken and the egg problem, in that even if a asteroid resource company was able to go out there and grab an asteroid and extract some metal or whatever from it, they wouldn't have a functioning business because there aren't any customers who are stood up and ready to accept those resources and pay for them. So we see what's called OSAM, on-orbit servicing, assembly, and manufacturing, as kind of the keystone that can help tie together these multiple markets and create a functioning economy where, say, $1 invested in one of these companies can flow around and around inside this in-space economy and turn into, hundreds or thousands of dollars of net economic activity. The challenge, but the overall challenge is that you've got to bring up both the supply side and the demand side of that economy in unison, and that's really challenging. Right now, we and a number of other organizations are working on kind of the supply side, developing the technologies to provide these in-space services, but the customer base is not there yet, and they're the customers are very reluctant to design their satellites or design their space systems to use these in-space services because those services are not yet proven. So, there's this overall challenge of how do you get a customer to sign up to use your in-space refueling service or whatever if you haven't already proven that in-space refueling service, and then how do you get the funding to prove out that refueling service unless you've got a customer who's signed up for it. So again, it's kind of this chicken and the egg problem that we and other people are trying to work through. So in the area, in space services, there are three main areas that we have been working on. There are a few others, but these are the areas that we've been focused on. In-space servicing would involve using a robotic spacecraft to refuel other spacecraft, to recover a spacecraft that might have had a problem during an antenna or solar panel deployment, and repair spacecraft that have had damage or failures on orbit. And the net benefit of those capabilities to the industry are enabling new kinds of missions, such as ones that require persistent maneuvering of a spacecraft throughout its entire lifetime, as well as being able to support long-term sustainability of operations in low Earth orbit by doing things like cleaning up space debris. In-space assembly of modular space platforms and on-orbit integration of upgrade payloads can provide the net benefit of improving the responsiveness of space systems to rapidly changing market and mission demands. Where right now, typically a large spacecraft takes 3 to 5 years to build, and it costs several hundred millions or even $1 billion to get up and functioning. But then a few years later, 3, 4, 5 years later, the technology on it is obsolete, and there are a whole bunch of geosatellites that are up there that are money losers because their technology is already obsolete. Yet they have 10, 15 years of lifetime left. If we can upgrade their payloads on orbit, we can make them more responsive to changing technology and changing market demands. And then in-space manufacturing involves launching into orbit raw materials in a compact, durable form, and then using tools such as 3D printers and robotics to transform those materials into support structures, antennas, solar arrays, and hopefully eventually entire systems. And if we can do that, we can escape the constraints of the launch shroud, where right now everything you put into space has to fit inside a launch vehicle. If we can manufacture them on orbit, we can make them much larger. So we can make larger antennas, larger solar arrays for higher power systems, higher data throughputs, higher sensitivity. So the net benefit of in-space manufacturing is to increase the net performance per dollar of space systems and continue to make them economically competitive. So I'd like to quickly run through a handful of projects that we have been working on related to these areas. First group I'll talk about is related to in-space servicing and in-space assembly technologies. And a lot of the work that we've been doing is right now coming together under a new project that we're just getting started on called GAUNTLET. And GAUNTLET is going to be an integrated robotics payload for MakerSat class spacecraft. And it's basically very similar in concept to the robotic payloads being developed for the DARPA RSGS system and the OSAM-1 mission. But those missions, those robotic payloads are very large, very heavy, require large, heavy, expensive satellites to support them. So they end up with a system cost, on the order of $500 million to $1 billion, which is, challenging to make a viable business out of, especially as a lot of the industry is migrating quickly towards small, low-cost satellites. So what we're trying to do is create a small, lightweight, and cost-effective robotic solution so that it can be economically viable for doing things like in-space assembly of multiple microsat class modules to create a large space system, or post-mission disposal or servicing of the smaller, low-cost small sats being deployed in the proliferated LEO architectures. So this system will integrate robotic arms, tool changers, and software that we've been developing. I'll talk about those over the next few slides. And here we're illustrating the key components of that payload: the robotic arms, tool changers, so the arm can swap out, grippers and screwdrivers and other stuff that it may need, and then software to enable control of multiple robotic arms and collaborative behavior between the arms and the satellite platform that they're riding on, as well as client vehicles and payloads. So the KRAKEN arm is a compact, affordable robotic arm that we've developed over the past 10 years. You can see in the upper right there that it stows into a very compact form factor, so it can fit onto relatively small spacecraft, but then extend out to give you about the same reach and dexterity as a human arm. The key differentiator with the KRAKEN arm compared to some of the other small robotic arms out there is that it integrates very precise torque sensing and control, as well as a very high-speed data backbone. So we can implement some new, very advanced control strategies, such as what we call active compliance, and I'll show you what that means in a few minutes. But the net effect is it enables the arm to operate safely around around spacecraft, as well as to enable a very lightweight, low-cost arm to safely manipulate very large, heavy objects. I'll try to illustrate that in a few slides. So one of the projects we worked on has been integrating one of those arms into a payload that can go up onto the space station. That payload would be called MANTIS. And the idea here is to offload repetitive and menial duties from the astronauts, so that instead of having to, wait for several months for an astronaut to spend 5 minutes, doing some simple operation on your experiment on the space station, you can just have a, $15 an hour grad student on the ground who's servicing that payload on orbit. And in developing it for the space station application, we had to do a lot of work to make sure it would be safe to operate around astronauts and in the same crew volume as astronauts, and that's where the active compliance comes in. So this is a video of a test demo that we did in our lab on a mock-up of a space station express rack. So here the arm is going through a sequence of moves where it might be pulling a metallic part out of a 3D printer and moving it over to an inspection station or something like that. On the upper right is a display of the control software that we use. But this would be operating inside the crew volume, and oh no, an astronaut has drifted into the way of the arm. A normal robotic arm on the ground would either lock up when it senses a obstruction, or it might just keep moving, which would injure the astronaut. But this KRAKEN arm actually senses the obstruction posed by the astronaut and complies with it. So we can very precisely control and limit the torque that the arm is, that each of the joints is applying. So it can comply with the astronaut, he can push it out of the way, and then the arm can go back to doing what it needs to do. For in-space servicing and assembly applications, we believe this will also be very, very useful, because this active compliance will enable the arm to accommodate velocity and attitude and position errors during, capture and manipulation of client spacecraft, because we can control the overall stiffness of the arm. So, when we initially grab onto a client, the arm can be relatively floppy and accommodate relative motion, and then we can controllably ramp up the stiffness to bring any motion errors, or relative motion, to a graceful halt and minimize any peak torques or forces on the arm, the host vehicle, or the client spacecraft. To enable the arm to use a variety of different tools, we've developed a compact hot swap tool interface. Key thing about this one is it is androgynous, so that both sides of the connection are the same. And what that means is we can also use this as a mounting point for the arm or for other hardware. So you could have a bunch of these mounts around inside a space station or on the outside of a space platform, and the arm could inchworm around to access different areas, and other systems like a free-flying spacecraft could dock to them to get recharged or other services. To enable in-space assembly of modular space systems, we've also developed a larger version of the AXON connector. This one is also androgynous, so that both sides of the system are the same. Here on the upper right, you're seeing some videos in the lab of the prototypes activating and connecting together. So the idea here is to provide a standardized connector so that not only could you rapidly integrate a payload before launch, but then you could swap it out for upgrade payloads or new payloads during the mission. And we've also done work funded by DARPA looking at architectures for ways to build large, high-performance systems, but do so by assembling a number of small, relatively low-cost modules together. And we've developed an architecture where each of these modules can be single string or limited redundancy to keep their costs very low. But by the way we connect them together and share resources and share data and commands between them, overall the system can achieve very high reliability and high uptime. And then when we have these servicing spacecraft interacting with clients and payloads, as well as these modular space systems, we need software to be able to control it and get these different systems interacting together collaboratively. So we've been working with the Air Force Research Lab to develop software we call SILON, which is intended to enable collaborative behavior between multiple robotic arms and the attitude control and thrusters on a host spacecraft, as well as client spacecraft. So this is a simulation that we've done in a multi-body dynamics simulation platform. Is this going to run? I'm going to have to scrub through it. So this is a servicer with two robotic arms that reaches out and captures the client, pulls off a spent propulsion module, throws it away, and then grabs the replacement module and sticks it on. then it folds up and goes away. And what's happening here is the SILON software is controlling the arms and the attitude control system of the spacecraft collaboratively to minimize the dynamics in the system, and to get the connectors of the arms where they need to go to latch onto things, even though the attitude of the spacecraft will vary as you move things around. Additionally, in the simulation, those arms each weigh about 7 kilograms, and this propulsion module is a ESPA Grande class payload, so it's 320 kilograms. So this software and that active compliance capability is enabling these small, lightweight arms to safely and precisely manipulate very large, massive objects. And then when you have these, modular space systems and servicers and clients and payloads, you need to have a way to exchange data between them effectively and easily. So we have been developing a mesh network communication system. It's basically an app that runs on our software-defined radios to create a peer-to-peer mesh network between multiple satellites, multiple modules, and enables data to be passed between them using standard IP protocols. So it makes it very easy to create a intersatellite mesh and manages the data routing and security and all that on the system. And then in the area of in-space manufacturing, we've been working on those technologies for a while. One thing you need to worry about or think through is, how do you get the material that you use to make stuff in space? Initially we'll probably launch the raw material from the ground, but there are resources out in space that we can use. One of the first resources we can use is trash, space trash. So we've done several projects looking at recycling of plastic waste on the space station, and shown here is the Refabricator payload that we flew on the space station. It combined a plastic recycling system with a 3D printer to demonstrate closed loop manufacturing and recycling of plastic parts. And it was intended as an experiment to kind of go through that a number of cycles and see how the plastic changes in the space environment as you print it and recycle it and print it and recycle it, so that when we someday send astronauts off to Mars, instead of having to send them with many shipping containers full of replacement parts for every possible failure mode or every tool they might need, we can instead send them with a 3D printer, recycler, and a spool of plastic, and they can, on a just-in-time basis, create the parts that they need. And the Refabricator was intended to see how many times they could recycle stuff before it wouldn't be printable or, reliable for whatever role it needs to play. We've also looked at, done some work on developing capabilities for recycling of space debris. And specifically, we worked on a project where we were developing capabilities to have a payload that would ride on an ESPA ring. ESPA ring is a big aluminum ring that goes between a rocket and a satellite, and you can put a bunch of secondary satellites on the ESPA ring. And that ESPA ring typically becomes trash that then you have to get rid of. In this project, we looked at a way of actually chewing up most of that ring, melting down the metal and remanufacturing it into segments for a large antenna reflector, and then assembling it together and creating a functioning communication satellite from that recycled material. We've also worked with NASA on a project called FabLab, which is intended to provide a capability for precision manufacture of metallic parts on the space station or future manned missions, for mission critical applications where plastics aren't going to suffice. Our part of that was integrating the KRAKEN Robotic Arm, the MANTIS system, and then inline quality assurance capabilities. And currently, we're working with NASA and Maxar to prepare an experiment called MakerSat, which is going to demonstrate on-orbit manufacture of a 10 to 20 meter long carbon fiber composite boom on orbit. On the left there is shown a stop motion video of an early prototype of what we call a trusselator, which is fabricating a carbon fiber boom from carbon fiber feedstock. And on the right there is an animation of the MakerSat manufacturing a 10 meter long boom, and then the robot, or the satellite's robotic arm could pick it up and wave it around like a giant lightsaber. So the experiment, the MakerSat payload also integrates metrology and inline verification of this beam that we're going to be manufacturing. So as we manufacture it, we're going to be vibrating it and bending it slightly so that we can verify that the composites that we manufacture on orbit hopefully have similar or better performance than the composite structures that we manufacture here on the ground. But basically the intent here is we're demonstrating that we can on orbit manufacture the 2x4s that we need to build large space infrastructure for things like large antennas or habitats or exploration spacecraft. And that's kind of a quick rundown of the slides that I had. Let's see, out of that. And I will stop. How do I stop sharing?
I think you can, yeah, there you go.
There we go.
Very good.
Yeah, so I'll be happy to answer any questions about that stuff. And I could kind of riff about my experiences in founding and building a space company, although things are changing pretty rapidly.
It has changed
out of date
significantly since you started in 1994 too.
Yeah.
Could you speak maybe a little bit to why you started a space company in 1994, what you were thinking then, and how things have changed?
Why I started it? Well, I didn't really know any better. I co-founded the company with Robert L. Forward. He was one of my favorite science fiction authors, and he spent most of his career working for the Hughes Research Lab. Basically we decided to form a company so we could try and pursue an unconventional space technology called space tethers. And we got lucky and landed a couple of NASA small business contracts early on that helped us get started. And I did that mainly because I wanted to work on something cool and unconventional, and that might have the chance to dramatically improve how we do space missions, reduce the cost, improve our capabilities. The space tether story has been a really long, frustrating road. I've kind of had my heart broken several times where we've been very close to landing $100 million plus missions to demonstrate some really awesome stuff, and then two government customers start squabbling and the thing falls apart. But it's taken 25 years, but we do have some of our tether technology on orbit and in demonstration, and we are working towards another very cool space tether mission right now. But because funding for space tethers was very up and down, and because I had interest in a bunch of other areas, we branched out and branched out maybe a little bit too far. But back in 2007, we did one of the first privately funded CubeSat experiments. We flew 3 low CubeSats to test out one of our space tether technologies, and that kind of got us some credentials and experience and perspective into the potential small sat market. And based upon that, we started developing components for CubeSats and small sats, and that's how we got into software-defined radios and thrusters and gimbals and deorbit mechanisms and that sort of stuff. And that in that we were, either had good foresight or we were lucky, and we were kind of pretty well positioned to ride the small sat revolution. So we've seen good growth in our small sat components part of our business. So right now that's maybe about half of our business is doing radios and thrusters and those sorts of things for small sat missions, and we're hoping to continue to grow that as SDA and commercial entities and DoD and other folks are all trying to develop these constellations of low-cost small sats. But we've also always tried to develop new capabilities in other areas. And about 12 years ago, we started working on capabilities for in-space manufacturing and robotics for these in-space services. And that has also been a good growth area for us. Most of those, or pretty much all of those, are still kind of in the R&D and demonstration stages of their life cycle. They're not yet operational, but we are working towards a couple of flight demos that'll move those technologies closer to being truly on the market.
So,
go ahead.
Well, so you're mentioning OSAM technologies, and the OSAM 1 mission has been in planning and development for a number of years, and I guess it's expected to go up, next year?
No, it's...
Or 23?
It's been, I think they're talking 24, 25. I think a lot of that is driven by NASA's funding constraints. The program that's funding it only has a certain amount of money every year, so they're kind of stretching out the. We'll be delivering our flight hardware in about 6 or 8 months, but then it's gonna sit on a shelf somewhere for a few years before it gets onto orbit. So it's kind of frustrating, but
yeah, that can be frustrating.
That's kind of how it is.
I'm curious if you have thoughts about how rapidly the OSAM technologies are developing, independent of what NASA is doing. So like we observed, NASA's development of the OSAM 1 mission has been going rather slowly, and I see you and other companies rapidly developing technologies. So do you think that those companies will demonstrate even before OSAM 1 flies, or just how do you see that market developing?
Well, it kind of depends on the in-space manufacturing area. I'm worried that somebody else is going to beat us to the somebody who goes and gets some VC money and is able to just go real fast and not have to wait for NASA may beat us to the punch. So we're looking for other opportunities to fly our stuff through on other missions. But the big, one of the biggest overall changes in the space industry over the course of my career is that, when I started out and for the first 10 to 15 years, the government was kind of what, set the whole story for the space industry. It was all driven by NASA and DoD. But over the past 10 years, that has flipped to where, really industry and, commercial ventures are really setting the story in space. And NASA and DoD are struggling to keep up. So, in the OSAM area, one of the biggest things was last year that Northrop Grumman's Space Logistics subsidiary, successfully, so far they've done it twice. They've sent up a life extension vehicle that has latched onto a geosatellite that was running out of fuel and enabled it to keep operating, keep generating revenue, and that that was pretty much all commercially driven. So that has given the whole OSAM area a lot of credibility. and helping to move things forward. The other big driving function is just, our the space race. The space race kind of went away when the Soviet Union fell out of style. But now China is very active in the space domain. Their space program, doesn't get its priorities changed every 4 years. They've got a 20-year plan, and they're executing to it, and they're doing it, and they're landing tanks on Mars, and they're moving forward. And our whole, our DoD and NASA is, they're trying to figure out how to get out of their own way and keep up with the pace of China's advancements. So I think and hope that we and they will figure out how to do that and get things moving forward faster. But I can tell you that the government contracting process is still just a soul killer. Contract stuff that should take a week, it take 9 months. Anyway.
It's challenging, yes.
Yeah.
I see some folks are putting questions in the Q&A box, so let me read some of those. If there's a fear of VC-fueled competitors beating you to the punch, are you exploring that option instead of just relying on government contracting?
Well, no. Several times over my career, I went and tried to sell VCs on stuff we were doing, but I never had any success. And it just boggles my mind at seeing some of the stuff that's getting funded these days. So I gave up on VCs, and a year ago we sold the company to a private equity backed company. That's a different beast, and I'm still kind of learning the ropes, how to work with the private equity guys. They have a very different mindset. Whereas the VCs they're willing to take huge gambles on speculative stuff that might have a chance of turning into a unicorn. The private equity people, they will invest in acquiring revenue streams and expanding existing revenue streams, but they don't take it's I wouldn't say they don't, but it's very difficult to get them to invest in speculative new stuff. Like OSAM. That's kind of a struggle that I have right now, is that I don't have customers who have signed on the dotted line for in-space refueling capability, so I can't get, it's difficult to get private funding for those new capabilities. But now we're starting to get some traction with the government on some of those capabilities, and that is starting, I think, to get some of those wheels moving. But it's a different game, a different mindset.
It definitely helps to have customers, for sure.
Yeah.
Another question. You mentioned the chicken and egg dilemmas between suppliers and customers. How do you think the adoption/development cycle will play out there? And I should mention, actually, last month we had Dan Faber present on the work he's doing with Orbit Fab and developing gas stations in space, where he is actually trying to prime demand, the demand side of the equation.
That's kind of what we have had to do in the past. In the space industry, having flight heritage is this really key barrier to market adoption of your technology. So like when we first developed our radios, we had to, we basically invested and lost our shirt in getting a couple of radios into somebody's hands so that they could put them on orbit. But just getting those radios on orbit, gave us the credentials to start selling radios into the market. In the in-space services arena, I have, part of what I'm trying to do is to bring up a customer for the service in unison with the service. That takes a lot of juggling, but that's what we're trying to do. What's more likely to really happen is someone will just go and do it because some business case or some DoD mission demands it. And then once it's done, everyone will jump in. Like I said, a year ago, Space Logistics demonstrated the life extension vehicle. And now I can't count on one hand the number of new startups who want to do exactly that same thing. So they're, once it's demonstrated as being viable, then the industry starts to adopt it, and you see money flow into that area. But it kind of takes someone with stubbornness or the balls or whatever to just go do it, to kind of show everyone that it can be done. Like reusable rockets. People talked about that for 50 years, but nobody did it until Elon just went and did it. And now, every rocket company is talking about, oh, we're going to do reusable launch vehicles.
Yeah, it is interesting to see how when SpaceX doesn't recover a rocket, that's what makes news now.
Yeah, it's mind-boggling how so quickly it has become just standard business. You land these two boosters next to each other. It's just just freaking amazing. But to kids these days, it's just like, yeah, whatever.
We expect that to happen.
Yeah.
So you mentioned Space Logistics MEV-1 mission, and one of the things about that is, of course, that's effectively a large space mission servicing a GeoBird, which is also a large satellite. Do you see there being more opportunity for servicing in the GEO arena, or in low Earth orbit, or elsewhere?
There is a clear business case in GEO, evidenced by what they went and did. I think GEO and cislunar space, there are definitely business cases and kind of mission cases that close. LEO is a little bit harder. In LEO, everyone's rushing towards the I can never say it, proliferated LEO thing, where they send up dozens or hundreds of thousands of very, very cheap satellites. And as a DARPA manager told me, nobody washes a paper plate. So those systems, if they die, well, they die. They launch another 10. Who cares? Where I think the opportunity is going to be is when enough of those things die and they can't get rid of them, that they've got a significant collision avoidance problem, and then there'll be a business case for somebody like Astroscale or somebody else to go along and grab those dead satellites and get them out of the constellation's way. I think that in a few years that business case may close. The other area that I don't know if it's going to close, but I think it will, is these small sats are great because they're low cost and you can crank them out and yada yada, but their performance is just limited by physics. They typically can only have an antenna that's yay big, or an optic that's yay big, and that just fundamentally limits the sensitivity or the resolution of data that they can acquire. And higher resolution imagery or other data is significantly more valuable. So I think there's a case to be made that we could leverage the economies of scale of the small sat market to mass manufacture a number of small low-cost modules, but then robotically assemble them on orbit to make a large, high-performance, high-value asset. So that's one of the approaches that we're continuing to explore.
And your development of the truss structure, I guess, supports that?
That was a project called the Trusselator.
Yeah. Well, in terms of that, that's a technology that supports being able to build structures that are larger than will fit in a fairing.
Yeah, exactly. And the MakerSat project is closely related to the Trusselator. NASA didn't have enough money for us to make a whole truss, so we're making one of the longerons for a large truss, but basically proving out the key technologies needed to go and to build the whole truss.
I'm curious how that technology compares with, for example, the ARKA technology that Made in Space is working on.
So ARKA is it's basically using a 3D printer to print a plastic truss. We early on looked at 3D printing to make these structures, but that kind of 3D printing has a couple of limitations. One is the structural performance you get out of it. Because you're building up that truss layer by layer, each of those layers is a shear, it's a fracture line. And the strength you get out of the thermoplastics is, it's decent, but it's not great. If you really want to build a kilometer scale antenna or something crazy like that, you need to keep the overall mass of the system at a reasonable level. You need to use the highest structural efficiency materials you can get your hands on, and that's why we have focused on processes that use carbon fiber composites. It has several other advantages. One is the processing power and speed can be a lot faster than 3D printing, but really the main thing is the strength and the thermal stability of those materials are orders of magnitude better. So I think their thing will, it'll be cool. It'll be it'd be a useful demonstration, but I'm dubious at how much thrusting that big 20-meter solar array they're going to make could take.
So you're describing that as 3D printing, which I guess is additive manufacturing. When you talk about building your carbon fiber arrays, is that also not additive manufacturing, or I guess I'm unclear on what the difference is?
They're all kind of additive manufacturing, but it's not.
It's not plastic.
Not really 3D printing. Well, it's carbon fiber thermoplastic composites. So we're using an extrusion or pultrusion process, and then to make the trusses, we use it's kind of like robotic assembly. So it's more akin to the way that carbon fiber airplane fuselages are made, with the filament layup, where they're laying up tapes and bonding them together. So we're kind of doing that, using a bunch of tapes, welding them together, forming them, and then getting those structures and welding more together to make the truss.
I have another question here in the Q&A box. Going back to the discussion around VC money and private equity, given that Tethers has been sold to a private equity firm, are you considering starting a new company, or are you planning to stay with Tethers in your current role, or how do you expect that to play out?
I'm staying with Tethers, and I'm going to be the principal investigator on a big new flight mission that we're just starting up. So I think I'll be quite busy for at least the next 3 years. I frankly, I don't think I have the energy right now to start a new company. I would need to take a year or two of sitting by the river to regain the energy to do that again.
I can understand that. Starting up a company is a lot of effort, for sure. Here's another question. I'm not sure I understand it, but what role does natural gas and utility play in this economy?
I'm not sure what the direct connection is, but those are two resources that are very valuable. And, with OSAM, part of what we're wanting to do is enable the development of resources that are out in space, available out in space, water on the moon, water and other materials on the asteroids, where, being able to source them in space, reduce the launch costs for getting stuff into space, but also, can create a new resource extraction economy out beyond the Earth's surface.
And the space resources economy is a subject that's close to my heart. Do you have any thoughts about where we're likely to find resources first and what that's likely to look like?
I think the lunar polar craters will probably be the first ones, explored and utilized. But there are, even though Planetary Resources went out of business, there are other companies like Transastra that are making really good headway on developing capabilities for getting and extracting resources from asteroids. So I don't know, could be a toss-up.
There are near-Earth asteroids that are energetically easier to get to than the surface of the moon.
Yep, but they only come by every once in
a while. Yeah.
Moon. Yeah, the moon's always there.
Are there other questions? Okay, I'm not seeing any other questions here. Oh, here's another one. Somebody asking, can you talk more about the Fabricator project? Specifically, what were the main / most important / most interesting lessons learned from that program?
Well, we did find out kind of the hard way that these plastic materials do behave differently in the microgravity environment on the space station. The experiment worked, but we did run into issues. We did not meet all of our scientific goals. We met some of them, but the materials did behave differently. We've also seen that, fortunately prior to launch, on the MakerSat program, where these carbon fiber composite materials do behave differently and require different processing parameters in the space environment than they do, here in the ground in an atmosphere. So you do need to, you need to test these processes in very relevant environments before you fly them.
That makes sense. I realize you've sort of moved beyond it these days, but since it's where you started, could you talk a little bit about the tether technologies and how they were used and maybe what happened to those technologies?
Sure. So when I talk about a space tether is basically a long wire or cable deployed from the spacecraft. And there are a variety of different ways you can use them to move things around in space without having to consume propellant. If it's a wire that's got a conductor in it, you can drive current along the wire, and that current will interact with the Earth's magnetic field to give you a Lorentz force, which will push on the tether and push on your spacecraft. So you can maneuver around in low Earth orbit without having to burn up propellant. If you've got a high strength cable, you can, rotate that around a spacecraft and use it to fling a payload from one orbit to another, or even drop a payload down into a reentry trajectory. And then you can also use tethers to tie multiple spacecraft together into a formation, so they can hold a precise formation without having to continuously fire thrusters. We've worked on a wide variety of concepts. A lot of the work we did early on was focused around end-of-life deorbit of spacecraft to address the space debris problem. the work we did back then was frankly 25 years ahead of the market. And we never sold anything there because nobody really gave a damn about space debris or end of life debris mitigation back then. That has kind of come around, and we developed a simpler, lower cost implementation of that idea, and we've sold some of those, and we have those flying and working on orbit. We're still working on getting an opportunity to fly a electrodynamic tether for propulsive maneuvering. As I was saying earlier, a couple times we came very close to landing big missions to do that, but they kind of fell apart. That the whole tether technology is kind of like, has a life cycle, kind of like the cicada, where it gets popular for a while, there's funding for it, and then something happens and it goes away for 10 years, and then 9 years, after 9 years, I say, I'm giving up on tethers. I'm not going to work on tethers anymore. And then like the next day, some DARPA PM will call me up. Hey, Rob, I got money for you. Send me a 2-page white paper. And then I get sucked back into doing tethers again. So, we've made progress. Big challenge for a lot of tether ideas is, the population of satellites and debris in low Earth orbit is now so high that a lot of tether stuff just unfortunately is not going to be viable, because either the tether will run into something or it will get cut by debris. So I mean, the space elevator it's a lovely idea, but in my opinion, it's not viable around the Earth, because if you got a space tether extended out from the Earth, every object in Earth orbit is going to run into it sooner or later. And if you do the survival probability calculations, your $1 trillion investment is going to break pretty damn quickly. And unless somebody pays somebody to clean up all the space debris, I don't see that getting fixed. That being said, space elevator out at the moon or at Mars, I think could make a lot of sense and are worth pursuing. The big challenge all along, though, is that right when even before we were getting started, NASA flew a big space tether experiment on the space shuttle. They flew it twice, and they screwed it up both times, and that gave space tethers a real black eye. And even to this day, I still, encounter people at the higher levels of NASA, DOD, and FCC who, their immediate gut reaction is, "Oh, tethers don't work," and they won't even consider it, because even though there have been over 20 space tether experiments, 75% of which were completely successful, demonstrated all their mission objectives. There have been a handful of failures, and the space industry is just not tolerant of failure anymore. Contrast to the early days of rocket development, the first 20 rockets blew up on the launch pad, but people continued pursuing them. Tethers, unfortunately, have had a harder time, getting that acceptance and action. So it's been a long, pretty frustrating road with space tether technology.
It's one of those things that I think seems very cool, but then it has limited lifespan for the reasons I think you just outlined.
Yeah, there are a few niche applications where, space tethers do have a couple of killer apps, and we're working on one of those now. But they're kind of, they're niche applications. So,
would you consider the deorbit device to be one of those applications?
I think it could be, but it's not cut and dried. Most satellite operators, they're putting thrusters on their satellites, and they're just saying, well, we're just gonna, deorbit our satellite when we get down to 20% fuel, and they're they're getting FCC authorization with that plan. Where that runs into problem is when the satellite dies and you can't operate the thruster, then you got a dead satellite and you can't deorbit it. The tethers can help with that. So I do think they have, we are working on a very low cost version of the Terminator tape deorbit device, which is intended to be kind of a redundant backup deorbit solution, for when your thruster dies. But the challenge with that is, if it's a backup solution, it's got to be really lightweight and really low cost. So how do we get it to be ridiculously low cost and still make a profit, make a business out of it? That we're still working through.
Well, one approach is to do something along the lines of what Altius Space Machines did with the dog tags. So they have a contract with OneWeb to attach dog tags to every single one of those satellites.
Yeah, and we would love an opportunity like that. Yeah.
I think we have time for about one or two more questions if anybody has a question. Oh, here's a big one. I'd be very interested to hear anything more you can share regarding the novel differences found when recycling/extruding polymer material through your system in space versus the pre-flight on the ground testing that had been conducted. Also, how many full recycling extrusion cycles did the polymer retain sufficient structural integrity to meet NASA's usability requirements?
So the details of the differences in the material processing are kind of our key, IP trade secret stuff. So I'm not going to be able to talk in detail about that. In the plastics, the Ultem stuff we used, it got darker and darker every use and got more and more brittle. And its printing or its melting temperature changed. So with the setup we had, about 5, maybe 6 cycles was about what we could do. There's probably improvements that could be made by better control of temperatures in the process, further refinement of the process. But it was about 5. It would be a good rule of thumb.
Is that a limitation in the material itself, or could that be overcome with a different material?
Some of it is the material. These high temperature thermoplastics, when you get them up near their melting temperature, they start making more links between the polymer chains, so that that just changes the flexibility and brittleness of the material. But as I said, some of that is the process. How long you're heating it, how quickly you ramp up and ramp down the process, how else you might be abusing the material. So, like I said, there's probably further refinement that could be done. But at least that particular material, I'd be surprised that you could get it much beyond 10 cycles before you got to throw it away.
And then once you've essentially used it up, what do you do with the material? It's hard to throw away things in space without creating orbital debris.
Well, that stuff can make pretty good radiation shielding because it's got a lot of hydrogen in it. So one of the good uses of trash on the space station is as recycling. I've heard of one group that's basically making fancy super high-tech trash bags that the astronauts can stuff trash into and then hang on the outside of the space station. And it's like leaving your dumpster out in front of your garage, but it provides some radiation and micrometeoroid shielding in the meantime.
That's an interesting repurposing of the material. Very cool. Well, Robert, I really appreciate you coming with us, being with us this evening, and talking a little bit about Tethers and your experiences with the space startup. So thanks for coming to New Space Chicago.
Okay, thanks for the invite, and thanks to you all for coming out and listening. Thanks for your questions.
So I am going to, yeah, here we go. Just show a couple of screens here. So, sorry, that's the wrong one. Let's start with this. So, some of the upcoming events for New Space Chicago. This event tonight was our final one of our spring speaker series for 2021. So we are going to take a break over the summer and are planning to return in the fall with a new series. We are still deciding whether or not we will use the virtual format with Remo that we're using tonight, or whether we'll return to in-person format. In fact, we'll probably have some combination of both. So look for that starting in September. Then in October, New Space Chicago will once again be the local lead for this year's iteration of the NASA Space Apps competition. And that will take place the first weekend in October on October 2nd and 3rd. So if you have if you have an interest in participating in a global hackathon to solve problems that NASA has presented, please drop by and participate. And then following the success of our Student Space Congress in April, at the end of April, we are planning to have the second Student Space Congress in April of next year, in April 28th and 29th of 2022. And this is an opportunity for high school, college, and graduate students to present space-related projects, research, and work to a broad public and industry-specific audience. It's always very interesting to see what the students are working on. And it need not be space technology. There are a number of different areas which are certainly space-related, and we welcome any of those submissions. As I mentioned at the start, New Space Chicago is a registered Illinois 501c3 organization. We do operate on your donations. Your tax-deductible donation helps support the entrepreneurial space industry in Chicago. You can go to the website at www.newspacechicago.com and donate individually, or there are two specific levels of sponsorship. You can be an event sponsor for $250 and sponsor one event, and your information and logo and so forth will be presented during that event. Or you can be a premier sponsor for $1,500 a year. Your logo and information and so forth will be presented on all events for that particular year. So we look forward to your support. So at this point, I'm going to return us back to the floor. We have about 10 minutes before the event ends, and so there's an opportunity to continue networking before the system closes. So again, thank you for coming this evening, and we appreciate your support.